Throughout history, ancient civilizations have exhibited a profound fascination with triangles, evident in their architectural and scientific achievements. The majestic pyramids of Egypt and Mesoamerica stand as enduring testaments to the geometric precision and symbolic significance of triangular forms. These structures not only served as monumental tombs and temples, but also reflected the civilization's spiritual beliefs and astronomical knowledge. Triangles played a crucial role in these cultures, particularly in the realm of astronomy. Ancient astronomers used triangulation, a method involving triangles, to measure celestial distances and chart the movements of celestial bodies. By observing the sky from different vantage points, they could calculate distances with remarkable accuracy, laying the groundwork for future astronomical discoveries. This work was part of their geocentric view of the universe, where Earth was considered the center around which celestial bodies moved above and over the Earth's flat plane. This interplay of geometry and astronomy highlights the ingenuity of ancient peoples and their enduring legacy in the fields of mathematics and science. Their work with triangles continues to inspire and intrigue us today, offering insights into their advanced understanding of the world and cosmology. Ancient astronomical tools like planispheres, astrolabes, and sextants were all built and used on the basis of a geocentric flat Earth to determine the distances to the sun, moon, and stars. Simple trigonometric calculations could be made between two locations to determine the distance to the sun. For example, one location might observe the angle to the sun at 84 degrees above the horizon, and a second location observes the same angle to the sun of 84 degrees as well. Using an established baseline distance of 500 miles for our example, they could triangulate the distance to the sun from each observation point. With the distance between the two observers known to be 500 miles, trigonometry can calculate the distance to the sun. With both angles of elevation at 84 degrees, the formula shown here provides the distance to the sun from each baseline point of observation. This calculation would give each observer a distance of approximately 2,391 miles to the sun, far from what we are told by modern astronomy, where the sun is said to be millions of miles distant in the heliocentric model. This method of using trigonometry to measure distance to the sun is far more reliable and repeatable than the random reasons and numbers given by heliocentric scientists over the centuries. For example, when Copernicus first published his astronomical theories, he figured the sun's distance from Earth to be 3,391,200 miles. The next century, Johannes Kepler argued that it was actually 12,376,800 miles away. Isaac Newton would later make the telling statement that, quote, "It matters not whether we reckon it 28 or 54 million miles distant, for either would do just as well." This shows just how random and unscientific these estimates truly were. In the next century, Benjamin Martin calculated between 81 and 82 million miles. Thomas Dilworth claimed 93,726,900 miles. John Hine stated positively 95,298,260 miles. Benjamin Gould said more than 96 million miles, and Christian Mayer thought it was more than 104 million. Recently, heliocentric scientists have settled on the figure of 93 million miles. All of these, however, are based on the rare, observed parallax of Venus and the Sun, with wildly differing assumptions extrapolated out from there. Triangulation and trigonometry, on the other hand, are precise and rely on straight lines of sight, where factors like atmospheric refraction, as heliocentrists might argue, have minimal impact on accuracy, if any. Thomas Winship wrote, "As the sun, according to science, may be anything from 3 to 104 million miles away, there is plenty of space to choose from. It is like the showman and the child. You pay your money for various astronomical works, and you take your choice as to what distance you wish the sun to be. If you're a modest person, go in for a few million. But if you wish to be very scientific, and to be mathematically certain of your figures, then I advise you to make your choice somewhere about 100 million. You will at least have plenty of space to retreat into, should the next calculation be against the figures of your choice. You can always add a few million to keep up with the times, or take off as many as may be required to adjust the distance to the very latest accurate column of figures. Talk about ridicule. The whole of modern astronomy is like a farcical comedy, full of surprises. One never knows what monstrous or ludicrous absurdity may come forth next. You must not apply the ordinary rules of common sense to astronomical guesswork. No, the whole thing would fall to pieces if you did. Regiments of figures are paraded with all the learned jargon for which science is famous, but one might as well look to the changing clouds in the sky and seek for certainty there, as to expect to get it from the propounders of modern astronomy. But is there no means of testing these ever-changing, never-stable speculations, and bringing them to the scrutiny of the hard logic of fact? Indeed there is. The distance of the sun can be measured with much precision, the same way as a tree or a house or church steeple is measured, by plain triangulation. It is the principle on which a house is built, a table made, or a man of war constructed. The sun is always somewhere between the tropics of Cancer and Capricorn, a distance admitted to be less than 3,000 miles. How then can the sun, if it be so many thousand miles in diameter, squeeze itself into a space of about 3,000 miles only? But look at the distance, say the professors. We have already done that, and not one of the wise men we have so often challenged has ever attempted to refute the principle on which we measure the sun's distance. Let him disprove this, who can. If ever disproof is attempted, it will be a literary curiosity, well worth framing.